Alright, hello everyone. Welcome to the FE Session Online Edition via YouTube. It's good to talk to you all again. Sorry we can no longer do the physical sections. These are just going to have to suffice for now. But we are always looking for improvement, so if there's something you think we can improve on regarding these, please let us know via the email, responding to the email that you received, or talking to us on Discord. Either works. So, without further ado, let's get down to doing some of these problems. I will be looking at some directly from the Mechanics of Materials PDF. You guys should all have that. And I'm going to be starting with problem number 1. Nope, let's have the pen. There we go. Problem number 1. So we have an element that is subjected to the plane stress conditions shown below. You guys will have a picture of this as well, but I will draw it. And I don't want to use purple. I want to use blue. Can I? Okay. So we have what looks to be like a box here that is subject to plane stresses. We have a compression force that seems to be coming from this way and this way. Sigma x and sigma x, and then tension in these two directions, sigma y, along with some shear stresses going in these respective directions. Sorry for my drawing skills. I'm still getting used to drawing on this particular device. Tau xy, tau xy. So that is what we're looking at here. We have values for our 3 stresses. Sigma x is negative 140 MPa. Sigma y is 205 MPa. And tau xy is 100 MPa. Alright, so those are our 3 values. There are actually 2 ways to solve this problem. I will go over both for you, though I would recommend you to use the first one that I'm going to go over, since it is a little faster and might save you some time on the exam. So, what is the first way to solve this problem? So, what you can do is look in your handy-dandy little handbook, and you will find that there's actually a equation that you can use to solve this, and it is explicitly for the maximum shear stress. Tau max, what is that equal to? Square root of sigma x minus sigma y divided by 2, and this whole thing is going to be, come on, this whole thing is going to be squared, and then we're going to add tau xy squared. Now this whole thing will give us, what we are looking for as tau max. Now we have values for all of the particular involved. We have this, and this already defined up here. So with that being said, we can go and immediately take care of this. If you plug in all of your values correctly, you will get tau max equal to roughly 199.4, which puts us around answer choice C as 200 MPa. Cool. let me quickly go over the second method on how to solve this, and then we can continue to move on. So some of you may be familiar. If you guys need to look at this one more time, I'll scroll back up. You guys can copy it down. You can pause the video if you want as well. Awesome. So the secondary method to solve this is actually using Moore's circle. So we're going to draw Moore's circle here. We're going to start off with a grid. So we need to get some reference points currently. So this is going to be our sigma axis and our tau axis. We have a sigma x, sigma y, and a tau xy. So we're going to use our two sigma points and our tau xy point to define two different locations on this graph. We're going let's do 205 and positive 100 and negative 140, negative 100 MPa. So let's go around. Let's say this is about 200, 100, and we'll say over here is about negative 140. Oops. That's negative 100. So now what we need to do is find the center. We can find the center by using this little formula, which is 1/2 the two sigmas plus added to each other. This will give us roughly 32.5 MPa. So we're going to call that, let's say right here. Let me to fix this point a little bit. It should be around here. So now what we're going to do is connect these lines like so. Move this one over a little bit. And now we have basically we have what our circle is going to look like. So we're going to now rotate this 360 degrees so we can get our actual circle. Again, forgive me for the drawing. Do my best. All right. So now that we have this, what are we looking for? We want to know the maximum shear stress, which is tau. So we want to know tau max. Where is tau max? Tau max is going to be way here. We also will have a sigma max and min. We'll have the min over here. And then we're going to extend this a little bit. Sigma max here. If you're asked to find either of these, you know where to find them now. You can find those using basically trigonometry and other algebra to locate where they are on this circle. But to get tau max in this regard, what do we need to do? Well, we need to know what the radius of this circle is, because if we know the radius of this circle, let's use red. We can find out how far up tau max is. This is r. So how do we find that? Well, let's take this length here and this length here. And basically do some trigonometry so we can get the radius. Or sorry, we want this length. So we're going to use this length and this length here. We know this length is 100. And we know this length is going to be 32.5 because that's where this point is. Or sorry, it should be 200 minus 32.5. So if we take 200 minus 32.5 squared plus 100 squared, Pythagorean theorem here, we can get this hypotenuse. We should be able to get an approximate value of 199. Again, I don't have a calculator on me. You guys can check that, but it should get you around a number close to 200, which will lead you to the answer again being C. So those are the two methods used to solve this problem. You guys can use either or. I would personally use the equation since it's a little faster than drawing the circle out. Plus, they don't give you any extra brownie points for drawing cool stuff. So, yeah, we'll leave that at that. If you have any questions, please leave them in the comments and I'll be sure to try and answer them. So this was problem 1. Nice. Okay, let's do our next problem now. Let's look at number 3. Looks like we're going to have a lateral strain. We're going to be doing problem number 3. We will do this, let's just make a new note. Okay. Mechanics of materials. All right, so we're going to have a lateral strain on this, looks like a box. So let me draw this box. All right. Okay. So we have a force coming out of here, Fx, and a force coming out of the back, also Fx. We are tasked to find... we are tasked to find the lateral strain. Okay. Strain, if you remember, is this symbol here. Epsilon. We know that the area of this is 0.04 square meters. Nice. Fx is going to be, 3,000 kilonewtons. Our modulus of elasticity is going to be 193 gigapascals. And our specific volume is going to be 0.29. All right. How are we going to do this one? Let's see what we got. There seems to be, let's see, what goes the handbook help? Equations for lateral strain. All right, there we go. Hooke's law. Let's see. Does anybody remember what Hooke's law is? Well, in the event that you are not remembering, I'll write it down here. Sigma x over modulo of elasticity is also equal to force x over E times A. Fx being the lateral, not the lateral, the tension force. Tensile. All right. Oh, I've made a mistake. This is not specific volume. This is Poisson's ratio. Okay. That's good to know. All right. What do we got? We want to find our strain correct, because we need to figure out we want the lateral strain. In this case, lateral, I believe they are talking about in this direction. I am not sure. That's why we need to use Poisson's ratio, because we need to find out the change in the object in that particular direction. We're getting the strain in the x direction will tell us the strain, from here and here. But if we want to know the lateral strain, we need to use Poisson's ratio. All right. If you want some background on the physics of that, you may know already, but as an object, unless its Poisson's ratio is negative, which there are some objects that do possess that, when you pull an object apart, let me correct this, the cross section will actually shrink in the other locations, such as the z and the y directions, dimensions. So if you extend the x, you make the x bigger, y and z have to compensate by getting smaller. And that's why when if you try and pull apart, let's say a little candy bar, the middle gets a little thinner. That's a mechanic of materials in that regard. So we actually have all of this information in order to solve this equation. So we can get the strain in the x direction using Hooke's law. So that's going to come out to be approximately 3.89 times 10 to the negative 4. Yeah, times 10 to the negative 4. That is the strain in the x direction. So now we want to find out what's the strain in the y direction. If we have our xy here, and that's z. Poisson's ratio, what you can basically do with it is you multiply it by your other strain, and it'll give you the strain in the other direction. So if we take our Poisson's ratio, multiply it by our E of x, we can get our E of y. Actually, the Poisson's ratio will be negative in this regard. Negative 0.29 times our EX. What's this going to give us? Approximately negative 1.13 times 10 to the negative 4. And if we look at our answer choices, the one that is most closely related would be answer choice B, which is negative 1.11. Sorry, negative 1.1 times 10 to the negative 4. And that is how we would solve that problem using Hooke's law and Poisson's ratio. All right, cool. With that being said, we can move on to our next problem now. I could just write on the same page, but I'll save them anyway. Let's not do that. Okay. Now we will move to problem number... I'll name these all later. Let's look at problem 4. Looks... Oh no, 4 is orientation. Okay. Not too sure how to do 4, which is why we'll do it. Problem number 4. Let's figure this out. Okay. So we have an object that looks very similar to the one in the first problem. A box. We have a compression force of sigma x and a tension sigma y. along with some shear stress, tau xy. Going in exactly the same directions as they were in the first problem. What? My tau's backwards in this one? That's okay. We want to know the orientations of the stress planes relative to the x-axis. This is our axis configuration. And let's get some values for these sigmas here. Sigma x is going to be negative 75 MPa. Sigma y is 110 MPa. Tau xy is 58 MPa. All right, now how do we find the orientations of the stress planes with this information? So to do this, there are again more formulas. But again, similar to the first problem, you can solve this both with Mohr circle and with formulas. I would always recommend to use the formulas as long as you know which ones to use. The formula that we use for theta in this regard to find the stress planes will be as so. 1/2 arctan. Let me make that smaller. Arctan of 2 tau xy divided by sigma x minus sigma y. Again, we have all this information, so it's fairly simple to calculate. This will give us roughly 2 values. One, if you have to assume your theta to be in 2 of the quadrants, since you can add 180 degrees and get the opposite quadrant. You're going to have to take into account both of them. So in doing this, you will get negative 16.04 degrees and 73.96 degrees, which, looking at the answer choices, you can get as D. The alternative way is to use Mohr circle again. Let's quickly assemble one of those. We have a point over here. What is it? 110 and 58. And then we have a point over here, which is roughly negative 75 and negative 58. Our center is going to be here. We know how to find the center. 17.5. Let me draw my circles a little better. Doesn't have to match up precisely. All right, circle. So we know we can call this angle here 2 theta as it rotates around the to make the circle. We can find this angle actually through using trigonometry again. Maybe label this as theta, this is tau. So what we want to do is find out what the angle is going to be as it rotates around to the other side of the axis. So if we also call this 2 theta, we can find out. This is a bit confusing if you guys also can see the solutions manual, but what it seems like is that they're taking 2 theta to be 2 separate values, one being 32, one being 148, which is 2 of what we are looking for. Again, I guess using trigonometry, you'll be able to find the 2 theta and then you'll divide it by 2. Let's see if we can replicate that. So this angle here, we know what the vertical distance is, we know what the horizontal is. So we can make it a right triangle. Where this value is 110 minus 17.5, and the vertical distance is 58. We want this angle, so we can do it has to be a tangent. Yeah. Which, if you will recognize, is very similar to what we just did above with the equation, only we're doing it directly with the Mohr circle, which makes it easier to follow. And then we're going to multiply this by 1/2 to get actually just normal theta 1. And then to get theta 2, we'll do the same thing, only we'll have a different triangle. Or we'll have to take what we have from theta 1, actually 2 theta 1, and 180 minus that. And that'll give us, let's call this 2 theta 2. That'll give us 2 theta 2, which you would divide by 2 and get your answer again. Does that make sense? Hopefully it does. Again, if you have questions, let me know in the comments. So that is how you do this with Mohr's circle. Use trigonometry to find one of the angles. Then again, 180 minus that angle, in this particular example, will give you 2 times the other theta, which you can then find by just dividing by 2. The equation is a little simpler, though if you don't like using stuff you don't understand, if you didn't understand it, then I would say go with the Mohr circle. But that is just that. Alright, nice. Nice. Let's see what else in here is a difficult problem. This one has to find the principal stresses. What is the elongation? Okay, let's do this one. Number 5. So, what is most nearly the elongation of the aluminum bar, cross section 3 centimeters by 3 centimeters, shown when loaded to its yield point? If we all know what the yield point is, we kind of went over that at one point during one of our last other sections. And we have the length as 2.5 meters. We have the modulus of elasticity is 69 gigapascals. And the yield strength in tension, what do we call that? Yield strength we'll call it YS. 255 MPa. Or let's call it sigma S. All right, so what do we have to do when we're working with material, or deformable bodies or mechanics of materials, which is the same class? Hooke's law is very important. It's probably going to be in your handbook, but if you've memorized the formula already, which is not very difficult, that is also great. Sigma is equal to stress over modulus of elasticity. So with this, we can pretty easily get this strain, and once we have the strain, the change of length, the elongation, is that strain multiplied by the original length. So, again, in the words of this problem, we are being asked for what is the elongation of this piece of aluminum with this cross-section when loaded to its yield point. Because it gives us the yield strength, we're able to do this directly, which is cool. It's a little simpler. So we can get our epsilon. I don't know if I called that sigma before, but I meant epsilon. Our epsilon, we can do our 255 divided by 69. Though we do have to be careful, this is in gigapascals, this is in megapascals. So we will have to change accordingly our units. Now if you do that, this is times 10 to the 6, this is times 10 to the 9. If we do that correctly, we should end up with 0.0037 as our strain. Cool, so now that we have that, let's throw that into our delta equation. For L is 2.5 times 0.0037. What is our sigma? Our delta, my bad. Delta will end up being roughly 0.00925 meters, or 9.3 millimeters. That is our answer, and we will choose B. Sweet. These are more simple than I expected. Well, I mean, if you guys are sitting through watching me anyway, I appreciate it. Thank you for your time. Also, one other thing I'm really hoping to hear back from is what would you want the length of these videos to be? I'm not sure. We might be able to only post ones of certain length in the beginning, but if we do decide to make them longer, what would be a length you're comfortable with? I'm not sure if we want to have you sitting through an hour-long video of just, problem on problem, so it could get boring since there's not really any communication. So I'd be interested to hear your feedback on that. Alright. If I have to cut this video up into separate pieces, well, it's going to sound kind of strange on different videos, me going through each of them, so I'm going to make them sound like they're all part of the same one. Let's look at problem number 6. Or how about 8? Let's look at problem 8. All right, we are given a shear stress. Let's use a different color because I'm tired of red. Tau xy is 35 MPa. And a shear modulus of 75 GPa. The shear strain is what? What is the shear strain? Shear strain this is most likely going to be tied to another equation, and shear strain is gamma, I believe. What can we do with this? Let's see. Looks like Hooke's law will be the savior again, as it is for most of the problems in this section. Luckily, that equation is not too complicated. Hooke's law for this case will be tau xy over g. Again, the easiest thing to mess up here is the units. Tau xy is going to be in megapascals, where this is going to be in gigapascals. So we have to take into account the difference there. This will give us roughly 4.67 times 10 to the negative 4 radians. So the answer choice for this will be B. In regards to the different types of Hooke's law equations, I know there's a couple of them. I'm not familiar with each and every one of them, though we definitely did use a different one there. Let me see if I can find that for you, so I can at least explain that much. So since you can only use Hooke's law for certain types of materials, that's why they have different types, because they change different things. Also for this one, we're looking for shear stress, I believe. Yeah, which in this case is gamma. Okay. I guess I'll have to leave you guys with this for now. Again, questions you can ask at other times or in the Discord channel, and we'll do our best to find the answers for you. Alright, let's do one more problem before we dip out of here. Man, I wish I could ask you all what you want to do. Oh, it's an interesting one, though it's not really worth it to do a whole problem on it. I'll do it here at the bottom. Which one of these could be a potential, this is number 9, which one could be a Poisson ratio of a material? Poisson's ratio. We have not 3.5, 0.35, 0.52, 0.55, and 0.60. Which one of these could be a Poisson's ratio? Give you guys a couple seconds. I'm just going to say one observation that I've can see is that these are all above 0.5. Even if I knew nothing about Poisson's ratio or materials, seeing that three of the answers fall into the same category, leaving one out, is a little telling. So just from that, you could think that letter A could be the answer. And that is very good prediction. It's a very good way to answer the question if you don't know what's going on. Because, believe it or not, that is the correct answer. Because there is a specific range for the Poisson's ratio. And it's usually always below 0.5. So with that, you can knock out those answers and you know that this is the answer. Also, you could also say, hey, they're all above 0.5, so that tells me something. Little trick. Nice. Yeah, okay, so let's do another one still, so we still got some time. Number 10 looks like something similar we did already. Oh, it is very similar. It's asking for the maximum shear stress. It's again, you would use an equation or solve the Mohr circle. Oh no, there's number 10. That was number 1. This is asking for the maximum shear stress. Let's see. Alright, let's do the last one, number 6. Don't tell me to get organized. Alright. We have what looks to be another box. This time it's vertical. Just giving us all the boxes today. Let's see if I can draw three-dimensional today. Alright, and we have a force coming down F. And also another force causing this thing to be compressed. What is the approximate maximum load if the compressive stress cannot exceed 9.6 kilopascals? So the compressive stress cannot exceed 9.6 kPa. We want to know what the maximum load is. What is F max, or what should F be if the stress cannot exceed this number? Alright, so based on what we've done the rest of the time, what do we think we should do? I heard it somewhere. Yes, we're going to find an equation for F max, because our handbook definitely will have that too. We're going to call this, what is this? This was the maximum, so we'll call it sigma of S. We can find F max by taking sigma S and multiplying it by our area. Did I give the area? Do we have that? I think we do. Oh yes, it's way at the top. I must have missed it. We have a cross-sectional area of 13 square meters. Multiply that by the area. So we'll take 9.6 times 13. This is in meters squared. This is in kPa. Units for this should be okay. We're going to end up with 124.8 kilonewtons, which is most closely comparable to 125, is answer C. So this one was just a formula. You take the maximum, since you asked for the maximum force, you take the maximum load and multiply that by the area, because it will be dependent upon what the area, or the area of your material or device you're dealing with. Be able to figure out how much force you can apply to it before that stress permeates throughout the entire substance and will cause it to pass that yield point on the stress strain curve. Right, and after it passes this particular yield point, after this line is this dotted line is linear, then it will undergo permanent deformation. All right. Well, I thank you all for sticking with me for these couple problems. It is definitely a different experience, but it's still fun making these, and I will definitely continue to do them if you guys are willing. So if you like what you saw, let me know. If you didn't, also let me know in the comments of this video or direct email to me. Both work. If you like this, if you think this will work, if not, why not? And if there's any suggestions, that would also be helpful. But I don't want to take much more of your time. I'll make sure to send out new materials for you for the next week, and I'll make another video to post on that next Friday. I hope you all enjoyed. Do take care.